Hello physicists. So last video we covered average speed and average velocity, and we defined, average velocity as the the uh, the change in the position over the change in time. Okay? So, if you wanted to express as a vector, then the change in the displacement over the change in time. Okay, simple enough. So we found out, we discovered that for a position versus, this is x and this is t. Okay, so for a position versus time graph, the average velocity is just the slope of the line connecting 2 points. So imagine an object moving in such a way that the position as a function of time is shown by this graph. Okay, so if I were to pick a point here, t naught, and then pick a point here, tf, then, just a ruler, then the average velocity will be the slope of this line, because it's the change in time over, the change in position, delta x, over the change in time. Okay, and that's exactly what this ratio tells us. It's just the slope of this graph. But we start to run into a problem because, as you can see from the actual graph, the motion is a little more complex than just a straight line. It's very curvy. And as a result, we don't really get an accurate picture of how our object is moving. So we have to find some way in order for us to fix this dilemma, because if we just use lines all the time and we treat everything as linear, we can't really do much physics, okay, with just constant velocity and, average velocity. And so we want to find a way to find the instantaneous velocity. So, what's the speed here? At some time t, what's the speed here? We don't know, okay? Because you need a second point in order to guess the average speed. I would say it's about the average speed, but that's not a really good estimate. But because we needed it so badly, we invented a new field of mathematics in the 1600s and 1600s, 1700s, late 1600s, I would imagine. We invented calculus, right? So this is where the calculus bit comes in, and what we can do is use calculus in order to solve this problem of instantaneous speed. Okay, so imagine time t. Okay, so let's have our t not equal to t for the sake of, for the sake of this exploration. Now imagine we have a second time, right here, t plus delta t, and this delta t is different from this one. Let's get rid of that. Let's get rid of this. Okay, so this is our new delta t now. All right, and we can get our average speed by connecting the line through it. Now, what we're going to do is find our change in position. Okay, so if we were to imagine this curve as x of t, it's a function, right? It's position as a function of time. So the change in position will be x of t plus delta t minus x of t. Okay, x of t plus delta t minus x of t. Okay, it's just the change in position over here. Now, that means that the average velocity, in the x direction of course, will be x of t plus delta t minus x of t, so that's our change in x over the change in t, delta t. Now, if you've taken calculus, this should look very familiar, but we'll go through the derivation again, just so we can appreciate how nicely this all fits together. Okay, so we have our delta t over here. Now, let's just move our point here. Okay, so we're changing our interval delta t. And so this is our new interval. So you start to see that the line is a little closer to the average speed. So, sorry, the instantaneous speed at that point, instantaneous velocity. It's a little closer, and you start to notice one thing. Okay, so what I'm going to do is zoom in on this section of the graph. So this is t, and this is t plus delta t. So this is our first line. Not a very straight line. I could use the ruler, but it takes way too long to align. So we'll just ad-lib this line. So we have this line over here, okay? It's kind of accurate, not really. But watch what happens as we decrease delta t. So this is our new delta t. We see that our line starts to approach this new line that literally just hits the point once. And this is secant line, that's what it's called in mathematics. It's approaching what's known as the tangent line. It's a line that touches the function at exactly one point and has the exact same slope at that point. And it is this tangent line that we're looking for. This tangent line has the slope of the instantaneous velocity. And in mathematically speaking, what we basically did is we took a limit. Okay, we took a limit. The limit as delta t approaches 0, meaning that as we decrease the delta t further and further, we can't directly plug in delta t equals 0 here, because then we'll be dividing by 0. But as we approach 0, this quantity starts to approach the value of the instantaneous velocity, and this is known as a derivative. This is the derivative. So the instantaneous velocity is equal to the derivative of the position with respect to time. In other words, it is the slope of the tangent line at that point. So if we were to try to find the instantaneous velocity here, it would just be the slope of this tangent line over here. So on and so forth for any point. So we no longer need an initial time and a final time, because by limiting the time interval to 0, we were able to find an expression for the instantaneous velocity, which is just the derivative. And if you have taken calculus, then it's very easy to compute the derivatives. And if you haven't, then there are a couple of rules, derivative rules, that are helpful to know. So I recommend you just go through those. I I can't, not going to cover those here because it's a physics class. I think I've made a calculus playlist a couple of months back. You can look at those. So there are a couple of derivative rules, but other than that, this is really where calculus starts to come in. Up to this point, we have just really been doing some basic physics, but here's where the advanced part comes in. We're looking at infinitely small rates of change to find out the exact rate of change at a point. So, all right. So thanks for watching. See you next time. Bye.